Hello and welcome to Unit 4, Math of Chem, Lecture A. We are going to be talking about the basics of equations and formulas today. Math of Chem is called stoichiometry. That's a big fancy word for it. It just means all of the math that has to do with chemical formulas or reactions. So it's nothing special or fancy, it's just a different word. There are four main types of inorganic reactions. So these are most of the compounds that we've been working with this year, things that are not carbon-based. Synthesis, decomposition, single replacement, and double replacement are the four names. You should memorize those. So synthesis is going to be exactly what it sounds like. We're going to take two small things and put them together to make one product. This is the general formula for it. A plus B yields C. So one part plus another. They could be two elements, they could be two compounds, they could be an element and a compound. But the key is that they join together to make just one product. So two reactants, one product, synthesis. The opposite of synthesis would be decomposition. You have one large particle that gets broken down into two or more smaller pieces. So general formula, C yields A plus B. So you have your one small piece, something happens, it breaks apart. These could be two compounds, they could be two elements, they could be an element and a compound. The key is that one piece for your reactant. One reactant is going to be decomposition. Single replacement is always an element and a compound yields an element and a compound. So you need to memorize that. An element, and how do I know this is an element? How do I know just A is an element? One capital letter. And a compound, how do I know that B and C is a BC is a compound? Two capital letters. What do we know about the first one? The first one's always positive, the second one's always negative. So I have an element and a compound producing an element. So here's the element and a new compound. So the A replaced the B. One thing got replaced. Now I know A must be something with a positive charge because it's first in this compound. Okay. When you look at whatever this first element is, you're going to look at it and see, can it only make positive ions or could it be positive or negatives? If it could be positive or negatives, it could replace either element. Usually it's something that makes only a positive ion, typically a metal, and it's going to replace the first element in your compound. Double replacement is always two compounds. Two compounds make two compounds. So if I look at this one and the A must be positive and the C must be negative, and I look at the second one and the B must be positive and the D must be negative, the only choices that I have for compounds over here are AD and BC. I can predict that because I can't put the A and the B together because you can't put two positives together. Like charges repel, opposite charges attract. So we just flip-flop the positive ions. Two things are getting replaced. Two compounds make two compounds. Examples using real elements of what this would look like in models. If I have just magnesium and nitrogen and I'm making magnesium nitride, two elements make one compound, two things, one product, synthesis. This next example, where I have nitrogen iodide turning into nitrogen and iodine, one reactant, two products, one compound breaking apart into two things. This is decomposition. It's split apart. Single replacement, an element, one capital letter, and a compound, two capital letters, makes an element, one capital letter, and a compound, two capital letters. So the zinc replaced the hydrogen, single replacement. And down here, two compounds making two compounds. Two or more capital letters plus two or more capital letters yields two or more capital letters plus two or more capital letters. We just switched the positive ions. The sodium replaced the potassium replaced the sodium, and we made our new compounds. If you look at the one with the models, these are going to be what we call balanced equations because our final product over here needs to be made with three magnesiums and two nitrogens. So we have to start with 3 magnesiums and our 2 nitrogens. The coefficient 3 in front of the magnesium here tells us that there are 3 pieces of magnesium. The nitrogen is diatomic, so the little subscript 2 tells us that it comes together always in these 2 pieces. If we look at this one with the models, same thing. The 2 is a coefficient. It says we have 2 pieces of this nitrogen iodide. So there's 2 pieces here. Each nitrogen iodide is made of 1 nitrogen, that's this darker purple piece, and 3 iodines, those are the 3 lighter purple pieces. This is how the compound is, so we have to take them in whole sets. We have 2 whole sets of them. That's going to give us our 1 diatomic nitrogen here, so 2 of the dark blue pieces, and 3 pieces of the I2, also diatomic, so they come in sets of 2, so 1, 2, 3. All of the pieces are accounted for over here. We have a total of 1, 2, 3, 4, 5, 6 iodine atoms on the left. So we have to have 1, 2, 3, 4, 5, 6 iodine atoms on the right. 1, 2 nitrogen atoms on the left, 1, 2 nitrogen atoms on the right. Along with types of reactions, we're going to have different classifications for the formulas themselves. So there's 2 big classifications that you need to know, molecular formulas versus empirical formulas. So molecular formulas are how these things actually exist. So when you have water, water is H2O. It is 2 pieces of hydrogen to 1 piece of oxygen. Or sodium chloride is NaCl. 1 piece of sodium to 1 piece of chlorine. Or glucose, C6H12O6. It is made of 6 pieces of carbon and 12 pieces of hydrogen and 6 pieces of oxygen. These are molecular formulas. Empirical formula is lowest term ratio. And this is what's important. This is the only thing that you have to worry about. If it's in a lowest term ratio, if you can't reduce it anymore, it's an empirical formula. So, for example, water, H2O, 2 to 1 is already a lowest term ratio. Water, H2O, molecular formula is also his empirical formula. Sodium chloride, NaCl, 1 to 1 ratio is a lowest term ratio. This would be both a molecular formula and an empirical formula. But glucose, C6H12O6, this 6 to 12 to 6 ratio reduces down to 3 to 6 to 3, 1 to 2 to 1. So this would be your lowest term ratio. That would be glucose's empirical formula. C6H12O6, molecular formula, CH2O, empirical formula. For the most part, things that have molecular formulas that are different from their empirical formulas are organic compounds. This happens to be an example of a classification that you should have learned in biology as carbohydrates. Carbohydrates, carbo, carbon, hydrates, water, typically have the empirical formula of CH2O. Carbo, carbon, hydrates, water. So carbohydrates typically reduce down to an empirical formula of CH2O. Let's look at these other guys. So water, we already said if this is his molecular formula, his empirical formula, same thing. C6H14, 6 to 14 reduces down to 3 to 7. So C3H7 would be the empirical formula of this compound. And our inorganic compounds, we typically wouldn't call them molecules anyways. We build them in lowest term ratio, 1 magnesium to 2 chlorides. His empirical formula is exactly the same. His formula and empirical formula are the exact same amounts. So that's it. You're just looking for lowest term ratio. If it has lowest term ratio, it's an empirical formula. Typically, they're multiple choice questions. They ask you to pick out the one that is an empirical formula. When we write formulas and we have those subscripts below them, they apply to the element directly in front of them. So this too only goes to the aluminum. As soon as we put parentheses in, this number is going to apply to everything that's in the parentheses. So So it's going to apply to the oxygen and to the sulfur. Because what this subscript 3 means is that I have 3 of these sets. But within the parentheses, that 4 only goes with the oxygen, just like our rules normally say. So there's 1 sulfur and 4 oxygens within the parentheses. The 3 to the outside means that we have 1, 2, 3 sulfurs altogether and 12 oxygens. So when I look at this compound and I count the pieces, I say that there's 2 aluminums, there are 3 sulfurs, and there are 12, 3 times 4 is 12, oxygens. This skill becomes really important for all of the rest of the math. You have to be able to count the individual atoms in your equation, or we're not going to be able to do the next step, which is balancing. Last thing we need to do for this lecture is learn how to balance chemical equations. So the first thing we're going to do is talk about what balancing means and then how to do it. Okay, so chemical equations show us the reaction. The things on the left are called reactants. The things on the right are called products. Make sure you learn that. The arrow is an action. So that arrow is telling us what happens. Reactants are the things that we start with. The arrow tells us the reaction itself. This is where the action's happening. The products are the things that we make or that we're left with at the end. Reactants, products, 2 vocab words, just learn them. The arrow shows the direction it goes. Typically we write our reactions from left to right because we speak English and that's the direction that we read. Sometimes that arrow will be backwards. If you have something and the arrow is pointing to the left, then you switch which are your reactants and which are your products. You're going to follow the arrow. The tail end of the arrow is the things that are getting put together. The arrow points at the stuff you make. All right, we already know these symbols from our states of matter unit. S for solid, L for liquid, G for gas, AQ for when it's an aqueous solution, and that means that your solvent is water. C means crystalline, which is basically the same thing as solid. Typically, the state is not that specific. There's a difference between true crystalline solids and other solids. The state typically just uses an S, but if you see a C, it also means solid. It just means that it's in crystals. We learned about these things called catalysts in biology. In biology, you probably called them enzymes. Enzymes are biological catalysts. They're things that help a reaction happen. The cool thing with catalysts is that they're not used up. They don't change at all. So they're not a reactant and they're not a product. So we can't really write them into the left and we can't really write them into the right. And when we balance equations, we don't count or pay attention to them at all. But if they want to show you that a catalyst was used, they draw it above the arrow so that you know it was used in there, but you know not to count it as actual pieces in the reaction itself. So in this reaction of magnesium burning with oxygen, making magnesium oxide, we have 2 pieces of magnesium and 2 pieces of oxygen. So over here we have 2 pieces of magnesium and 2 pieces of oxygen. This catalyst at the top is going to make it happen faster, but we don't have to count these manganeses or the oxygens on either side of our arrow. This over here, where you see the calories, we'll typically see joules. You'll sometimes see it listed just as heat. So this is telling you that heat is a product. If heat is a product, that means we're producing or making heat or releasing heat. It's exothermic. If heat is a reactant, that means you need heat, you're absorbing it, you're taking it in. That's going to be an endothermic reaction. So you can look for these hints in the equation. It will tell you whether your equation is exo or endothermic. In front of your compounds, there's sometimes these large numbers that we call coefficients. So these numbers in front of your compounds, the big ones, are called coefficients. So there's 2, and it's a mole ratio, so we're going to call this 2 moles of hydrogen gas plus 1 mole of oxygen gas produces 2 moles of water. Notice there's not a number 1 drawn in here. It's kind of like x and 1x. It's just understood that the 1 is there. These are the things that we change when we balance equations. You cannot change the subscripts to get an equation to balance because then you change what type of compound it is. The coefficients are the only things that we can change. The coefficients are the only things that you change. Only change the coefficients to balance an equation. Do not change anything else. Our equations have to obey the law of conservation. So that means however many atoms of hydrogen I start with on the left, I have to end up with that many atoms of hydrogen on the right. So typically what I would have you do is make a chart, and this is from the left side of the arrow, and this is the right side of the arrow. When I look at this equation, it says I have 2 pieces of hydrogen gas. So 2 pieces with 2 atoms of hydrogen each gives me a total of 4 hydrogen atoms. And I have 1 piece of oxygen, which is made of 2 atoms. So I have 2 oxygen atoms total on the left. Then on the right, I'm going to count the same pieces. 2 molecules of water gives me 2 times the 2 atoms in each molecule, so for a total of 4 hydrogen atoms. And then 2 times the 1 atom of oxygen in water gives me a total of 2 oxygen atoms. 4 atoms of hydrogen on the left, 4 on the right. 2 atoms of oxygen on the left, 2 on the right. These match. It obeys the law of conservation. This is a balanced equation. When you look at equations, the first thing you need to do is look for mistakes. Magnesium, metal, no problem. Oxygen, however, is diatomic. So the mistake here is that somebody forgot to put a subscript of 2. And notice that if I don't have this as diatomic, it looks like the equation's balanced, even though it's not. So you have to be careful. Up here, done correctly. Down here, not. So look for your mistakes. If you are writing equations for me and you're unsure, you're making up the symbols yourself, before you try to balance it, bring them to me and have me check to see if you form the compounds correctly in the first place. If you don't form the compounds correctly in the first place, you're never going to get the proper equation. So now, even though you see the coefficients up here, let me just show you what would happen if we make a chart. I have 1 magnesium on the left and 2 oxygens, and right now I have 1 magnesium on the right and only 1 oxygen. You're tempted to put a subscript 2 here, but you can't do that because magnesium oxide just is MgO, so we have to change the coefficients instead. That means we have to put a coefficient of 2 here. Once you do that, you have to change your chart because now there's 2 magnesiums on the right and our 2 oxygens. So now the magnesiums are wrong. We put a 2 here. That gives us 2 magnesiums. Notice that the coefficients stop at a plus sign and stop at an arrow. So it only carries through to the compound immediately in front of it. All right, the last example in our notes is turning a word equation into a balanced chemical equation. So this is a skill that you should have. And it's something that you're going to be expected to be able to do on your final. So potassium hydroxide, potassium symbol is K. It has a charge of +1. Hydroxide is OH. It has a charge of -1. Combines with, that's going to be a plus. Hydrochloric acid, you can look that up. Hydrogens have a charge of +1. Chlorines have a charge of -1. If you use table K to find hydrochloric acid, it's HCl. It's already written for you. 2 form is going to be your arrow. And then we're going to make potassium chloride, so +1 and -1, and water. And you should know water, it's H2O. So if we put this all together, we have potassium hydroxide, +1, -1, just 1 of each, because it's a 1-to-1 ratio. Combines with hydrochloric acid, that's HCl. 2 form is your arrow. Potassium chloride, +1 and -1, so it's a 1-to-1 ratio, just 1 of each. And water. And you know that water is H2O. So I formed all of my compounds correctly, and now I'm going to try and balance it. So again, I would make a chart with what's on the left and the right. We have potassium, we have oxygen, we have hydrogen, and we have chlorine. On the right side, I know they don't show up in that same order, but I'm going to write them down in the same order anyways so that I can match them up easier. So right now on the left, I have one piece of potassium, one piece of oxygen. Now the hydrogens become tricky because they're in two different compounds over here. So I actually have two pieces of hydrogen and one piece of chlorine. On the right hand side, one piece of potassium, one piece of oxygen, two hydrogens, and one chlorine. When I look, these all match up. It obeys the law of conservation. This is your finished balance equation, and you don't have to change any of the coefficients. They're just ones. Let's look at some other examples of balancing. Here it is in models. Sometimes looking at the models helps people. C3H8, if I were to do this as a little chart, I would have to say there are 3 carbons and 8 hydrogens. Oxygens, they have 5 oxygens. Oxygens are diatomic, so the 5 oxygen molecules gives them 10 oxygens altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens altogether on the left. On the right, 1, 2, 3 carbons. So this 3 is going to carry through. I'm going to look at hydrogens next. Here's a 4, which is going to carry through. So 4 times 2 is 8 hydrogens. If we look at our waters, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. This 3 is carrying through to our oxygen. So 3 times 2 is 6. Plus, this 4 carries through to our oxygens, 4 more, which gives us our 10 oxygens to match the other side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So sometimes it's easier if you're looking at the models when you first start to think about the number of pieces. But it's just like algebra where you had to learn how to carry the numbers through. You will get used to it. Let's look at some multiple choice questions that use balancing and see how this works. Okay, so when the equation is correctly balanced using the smallest whole numbers, we're always going to use the smallest whole number coefficients. They want to know the coefficient of just the NaCl. So we have to start by balancing this in the first place. So we have irons on the left and chlorines, sodiums, and carbonates. Now notice if this polyatomic ion stays together as the same polyatomic ion on that side, it doesn't break into pieces, we can leave it together in those pieces and just count the numbers of polyatomic ions. It makes things a little bit easier. So 1 iron on the left, 1 iron on the right, 2 chlorines on the left, 1 chlorine on the right, 2 sodiums on the left, 1 sodium on the right, 1 carbonate on the left, and 1 carbonate on the right. So my chlorines are wrong. I need 2 chlorines on the right-hand side, so I'm going to put a coefficient of 2 here. That changes my chlorines. It also changes my sodium, and now my equation is balanced. So if they want to know the smallest whole number coefficient for the NaCl, your answer would be 2. All right, number 2. Whenever you see reactions where you have an organic molecule, so something made with carbon and oxygen, these are combustion ones and they are hard. Typically, when we balance equations, the normal order you would go in would be metals, nonmetals, and then leave oxygen last. Sometimes you don't have a choice and you have to start with the oxygen, but if you have a choice, leave oxygen to the end. In the combustion equations, the oxygen, the O2, is always a singleton over here. Easy enough once you get your even number of oxygens and the other things are balanced to then put an even coefficient in front of here, any coefficient you want to get your even number of oxygens. Let's count pieces first. 8 carbons, 16 hydrogens, and 2 oxygens on the left. 1 carbon, 2 hydrogens, and 3 oxygens on the right. One of the things that makes these hard is that in the combustion reactions you always split the oxygens up, so it makes it difficult. I'm going to start with the hydrogens first. So I'm going to get 16 hydrogens here, I'm going to put a coefficient of 8 there. That changes my oxygens. 2 plus 8 gives me 10 oxygens over here. But I also need to get 8 carbons. So I'm going to put an 8 there, which changes my carbons to 8. It's also going to change my oxygens. So 8 times 2 is 16, plus 8 is going to give me 24. So notice that I didn't multiply this 10 by 8. I had to actually add up the oxygens over here, so I have 24 oxygens. Carbons are balanced, hydrogens are balanced. To get 24 oxygens here, that's going to have to be a 12. Definitely a more difficult equation to balance. A couple more examples. Number 3, when the equation is correctly balanced using the smallest whole number coefficients, the sum of the coefficients. You have to watch out for this. Sometimes in the questions, they don't ask for a specific coefficient. They want the sum, so they want you to add them all together. So we have aluminums, we have sulfates, we have zinc, and we have chlorine. So aluminums and sulfates and zinc and chlorine. So if we count first, there's 2 aluminums, there's 3 sulfates, there's 1 zinc, and there's 2 chlorines. On this side, there's 1 aluminum, there's 1 sulfate, there's 1 zinc, and there's 3 chlorines. We're going to change coefficients, and remember I said start with the metals first is usually the easiest way. So the only metal that's not balanced is aluminum, so I'm going to put a 2 here. That changes our aluminums. It also changes the chlorines, so now that there's 6 chlorines. The zinc is already balanced, so we need to change either our chlorines or our sulfates. So if I put a 3 in front of here to fix the sulfates, I've also changed my zinc. So now zinc is the metal. I have to go back and put a 3 here for that zinc, which also changes my chlorines. 3 times 2 is 6 chlorines. And now everything matches. 2 and 2, 3 and 3, 3 and 3, 6 and 6. This obeys the law of conservation. Be careful with this with the sum of the coefficients. When you look, your first instinct is going to be to add up the ones that you wrote. So 6 and 2 is 8. And of course 8 is a choice. But don't forget that there's a 1 in front of here. So the correct answer is actually 9. Some more problems in a little bit different format. Yeah, these didn't copy over very well. They've cut off, so we can't do number 6. Let's look at number 7. If an equation is properly balanced, both sides of the equation must have the same number of, well, if we just take any balanced equation. So let's make some water. I need to have 2 oxygens over here, so I'm going to put a 2, which means I need 4 hydrogens, so I'm going to put a 2 there. So I have a properly balanced equation. They have the same number of coefficients. Number 2. Do they have the same coefficients? No. I have 2 and 1 and 2, so it's not coefficients. It's definitely not the same. Molecules. I have 2 molecules of hydrogen and 1 molecule of oxygen. So it's 3 molecules on the left and 2 molecules of water on the right. No. Moles of molecules. 2 moles, 1 mole, that's 3 moles, 2 moles. It's the same as choice number 3. But atoms, that's what we're looking for. 4 atoms of hydrogen on the left, 4 atoms of hydrogen on the right. 2 atoms of oxygen on the left, 2 atoms of oxygen on the right. So it's always the atoms. They want to know the coefficient of aluminum when this guy is properly balanced. So we're going to make our chart, aluminum, copper, and sulfates. And aluminum, copper, and sulfates over here in our single replacement reaction. We're going to start with metals. 1 aluminum on the left, 2 on the right, 1 copper and 1 copper, and then I have 1 sulfate and 3 sulfates on the right. So when you look at this, if we start with the metals, which is what we normally would do, I can fix the aluminums, but since the aluminums and the coppers are singletons all by themselves, I can put any coefficient I want in front of them. So I'm going to start with the sulfates. I'm going to put a 3 here, which gives me 3 coppers and 3 sulfates. So now my sulfates are balanced. To fix my aluminum, I simply put a 2. To fix my copper, I simply put a 3. And now this one is balanced. They want to know the coefficient of the aluminum. The coefficient of the aluminum is 2.